Hello, this video is on interpreting numbers. When children start counting, the numbers are usually associated with physical things. They may be fingers, or people, or cars. Books and toys often also follow this pattern. Get a data frame of length 100. Now, right-click and duplicate x1, call it x1a. Now to our calculator, and first do x1 plus x1a, then x1 times x1a. So, in the column called calc, we see, for example, that 4 plus 4 is equals to 8, and 4 times 4 is 16. But we are not saying 4 cats plus 4 cats is 8 cats. It is just the number. So 4 of anything plus another 4 is always 8. As we work in tens, let's get some larger numbers. Then we will try to interpret them, starting in relation to other objects. Return to the calculator and use 10 to the power of x1. That gives 10, then 100, then 1000, and so on. At the bottom, it is close but not quite right. We saw this problem of accuracy in an earlier video. We solve it in the same way. We use the integer keyboard and the first key, then x1, and then the power of 10. That's better. With the previous column, we put it into scientific notation. Press I and then edit the false into true. You just need to type the first letter. Now, we see that the last row can be written as 1 exponential 100 or as 1 with 100 zeros. Now for some interpretation. Starting at the top, I can easily picture 10 just with my fingers. For 100, I sometimes watch athletics and can picture 100 meters. Now, what would you like for 1000? One interpretation is that it is a kilometer, but on a smaller scale, a meter is 100 centimeters and I can picture a centimeter, and that is 10 millimeters. So, a meter is 1000 millimeters. We can continue like this. For example, 10,000 in meters is a running race I sometimes watch. Another interpretation is my 100 meters both ways. As an area, it is a hectare. And I can picture a hectare quite well by thinking of it as 100 meters each way. So, 100,000 in meters is 10 hectares in area and 100 kilometers in meters or 1k in centimeters. And a million? In Britain, that's the cost of a really expensive car. Or it is 10,000 pounds if in bags of pennies. Or it is the 100 meters track in area, so a hectare. But also 100 meters high, so a 100 meter cube. Or it is a meter cube if measured in centimeters. But we are only as far as row 6. Is there any way we can picture a Googol? That is the last row and is 1 followed by 100 zeros. I'm not sure we can, but let's try. An atom is very small. So how many atoms in a grain of sand? Or I think a grain of rice would be similar. Well, it is estimated there are about 10 to the power of 18 atoms, so we are on our way. Now, how about you? How many atoms in you, roughly? Well, it is thought there are something like 7 times 10 to the power of 27 atoms in each of us. So, we can go down some more. And the whole Earth is estimated to have about 10 to the power of 50 atoms. So we are halfway down. Now, let's bring in the Sun, or perhaps the whole solar system. It doesn't matter which you consider because the Sun is so big that the rest of the solar system is just 0.2% of the volume of the Sun. That was a surprise to me because I thought the Earth was quite big. And then you add Jupiter and Saturn and all the minor planets and asteroids. So if that is 1,500th of the Sun, it really shows how ginormous our Sun is. No wonder it keeps us warm, even though it is so far away. Anyway, we are now down to row 57 with the Sun, or our solar system. So, the Milky Way, our galaxy, that has been estimated to have 10 to the power of 67 atoms. So we are 2/3 down our list. And we are not finished yet. There are lots of galaxies in the universe. And there are so many that it is estimated that there are about 10 to the power of 80 atoms in the whole universe. Amazing. But still lots less than a Googol. So, a Googol is 10 to the power of 100. Sounds innocent, but it is larger than the number of atoms in the universe. When a Googol was invented in 1920, the Googolplex was also sort of defined. This was stated by a 9-year-old as 10 to the power of zeros until you get tired. Now it is defined as 10 to the Googol. That is much bigger than just waiting till you get tired. Remember that 10 to the power of just 100 is more than the number of atoms in the universe. So 10 to the power of a Googol has more zeros in the power part than there are atoms in the universe. Let's be clear that if you could write a 0 on every grain of sand in the earth, and remember the Sahara Desert, then you would have written about 10 to the power of 18 zeros. So that's tiny compared to 10 to the power of 100 zeros you need to write. And that's just for the zeros, not for the number itself. So, are there reasonably simple numbers that are larger than a Googol? We have shown you can't just start counting anything physical because you'll never even get close. But that's not the only way to think of this problem. Let's start small. If there are 4 people and you want them in a line from left to right, then how many ways can you do this? Any one of the 4 can be the first person. Then you're left with 3, and any one of the 3 can be the next. That's 4 times 3 ways, which is 12. Then either of the 2 can be next, so that's 24. Then there's just one person. So the number of ways is 4 times 3 times 2 times 1, which is 24. That's what's called 4 factorial. We like games, particularly games where you have to think. Dominoes is a popular game and it has 28 pieces. You start by shuffling them, then you pick them in turn. Now you could choose any of the 28 as the first. Then any of the 27 that remain could be the second. So there are 28 factorial ways or orders for the set of 28 dominoes. There are many interesting card games with a standard pack. This has 52 different cards with 13 in each suit. We have our own pack with interesting puzzles on each card. In most games, you shuffle to begin the game. So any of the 52 could be first. You can see where this is going. There are 52 factorial ways that the cards could be ordered after a good shuffle. There is an interesting game called Set. This has 81 different cards. So, when shuffled, there are 81 factorial different possible orders of these cards. And finally, Let's return to our original problem, but this time with 100 people. That gives 100 factorial different orders. One aspect that is new here is that the number problem is the same whether it concerns people or dominoes or cards. It is an ordering problem for anything. For example, if we have 10 ingredients for a cake, then how many different ways could we include them? It's over 3 million ways, though you might not always get a good cake. We can do factorials, so add them to the data frame. Now we have an answer to the questions above. We confirm that with 4 people, there are 24 ways. The 10 ingredients could be ordered in 3.6 million ways. The 28 dominoes in 3 times 10 to the power of 29 ways. So that's more ways than there are atoms in a person. This is getting promising. The 52 cards can be ordered in 8 times 10 to the power of 67 ways. So that close to the number of atoms in our galaxy. And the 81 cards for the game called set can be arranged in 6 times 10 to the power of 120 ways. So that's considerably more than a Googol. We even complained above that the number of atoms in the universe is about 10 to the 20th less than a Googol. Now we have a number that is 10 to the 20th more. Ha! Of course, the 100 people can be arranged in many more ways than this. And going back a bit, a Googol is roughly the same as the number of arrangements of 70 items. Now I can sort of picture rearranging 70 items. So perhaps I can picture a Googol. Of course, I must not fall into the trap of trying to write them out in order, because then I'll never finish. And I don't think it'll help by getting all the people on Earth to write them out. Even if every atom on Earth could write them out, it wouldn't help. Just picture rearrangements instead. Some people do complain that a Googol is artificial. Some numbers are interesting because of their properties. So 6 is interesting because it is also 3 times 2 times 1. So it is also 3 factorial. Also, the divisors of 6 are 3, 2, and 1, and they add to 6. 6 is called a perfect number. But a Googol has such a nice name, and in our system of counting, it can be written as 10 to the power of 100. That's pretty real too. But let's finish with some even more interesting numbers. I know that there are an infinite number of prime numbers, and that means that however large your numbers are, there are always prime numbers that are larger. That's pretty amazing to me because there are so many smaller numbers that could divide into it, but they don't. Use the column with the exact powers and the integer keyboard again. Then the key for the next prime. Now that's fun. I knew that 11 was prime, and that's obviously the first prime that's larger than 10, but I didn't even know that 101 was a prime number, and it is just one more than 100. As we go down, there are no other examples where the next number is prime, but there are quite a lot with the addition less than 10. And the first prime that is larger than a Googol adds 267 to the value. So that's a look at powers of 10. In the next video, we'll examine powers of 2.